Okay, it's time to begin the afternoon session. It's my pleasure to introduce Greta Panova, sorry. Who will talk about Grothendieck Shenanigans as well as
Thank you very much. Thank you very much for the invitation. It's a pleasure to be here, and it's very interesting for me to be a part of an enumerative geometry workshop. So it's my main field is algebraic combinatorics, but with sort of different directions. And I wanted to tell you today, and that's also what our organizers asked me about, is how you can look at enumerative geometry questions from a slightly different perspective. Sometimes we don't have exact nice formulas to talk about, so there are two things you can do in those cases to understand your objects. One thing that we were discussing yesterday, and I like to talk about in other settings, is computational complexity theory. But this time we're going to talk about the other aspect, which is asymptotic behavior, large-scale limits, and probability. So I know that you're all algebraically minded, you know, that's not how you used to think about, but I hope I can convince you that there are some pretty pictures at least that you can get out of that. So, and that maybe informs you, can inform how you think about the objects in certain more qualitative, maybe less quantitative ways. Okay, so the talk today will be to explain what these pictures have in common. And before I start, I think I need to explain some parts of the title. So they will be explained in due course, but let me first tell you what integrable probability is, because that's not a very such a classical subject. It's a more recent one. It starts with statistical mechanics. If you're studying atoms that's on a lattice, so this is chemistry, guys. These are not posets or lattices. This is an actual 3D configuration of molecules that have some orientation and can connect in various ways. If you're in a lattice that it would have some structure, the molecules would be dimers, and you can simplify this, make a mathematical model. How do these dimers arrange themselves? Or going backwards, if you have a graph, in this case, it's going to be all 2D, so you have a planar bipartite graph. In how many ways can you do a perfect matching on this graph, or choose edges, so your dimer cover? And what kind of properties would this have in the limit? Because of course, materials have millions of atoms in there, so you want to see how this thing looks in large scale. And a lot of the times when you're looking at these dimers, there are different ways you can picture them. So now instead of looking on the hexagonal grid and looking at dimers, you can replace each dimer by a pair of triangles, which we call lozenges. That's when, like lozenges, when you have a sore throat, that's what you take. So, but in this case, it's like rhombi. We call lozenges, and if you color them differently, you're gonna get a 3D picture that looks like that. And for you, it's more familiar as a plane partition, right? Cubes in a corner of the box, so that's now a very combinatorial object. But then still you want to know how this thing looks like when you scale, and when you scale, it would look something like that. And then you start saying, there is some interesting behavior. In particular, this starts to look like a circle, then you have limit shapes, and there are random matrices come in the picture, and so on and so forth. So there is a lot of story going on here. So that's how things in integrable probability look like. Why is it called integrable? Because originally in the definition, it's basically some system where you have a Young-Baxter equation that actually came up yesterday in Alan's talk. But more informal is when you have some precise formulas like determinantal identities that would help you understand this in a better, more rigorous way. Let's put it this. Okay, so now I'm not gonna talk about lozenge tilings, but I will talk about some other types of tilings. So let's take a triangle, triangle composed of squares, and for each square we're gonna put one of these two tiles that should be familiar to you from Alan's talk. So these two tiles, and you can get a picture that looks like this. So what is this? This is a pipe dream. There is something special about this pipe dream. So it's not really you putting arbitrarily in the boxes these tiles. You have another condition. What's the condition? Is that no two of these pipes intersect more than once. And that's okay. So that, as you know, is a model for Schubert polynomials in certain very precise sense. You're connecting. So my convention is, so the pipes go from here to here, and that's how you read the permutation. So, but in this talk, it's not really gonna matter. So the condition for this is that no two pipes intersect more than one time. And then you can ask what just the total number of configurations possible, and forget about the permutation in the end. How many pipe dreams are there of size n? We don't know. And statistical mechanics integrable probability cannot really help here, because there is something called long-range interaction, in the sense that whatever happens here is going to affect whatever happens in the other way, because you have this no double intersection condition. So there are no tools really available to study things like that. So if there is, so here is a problem that is combinatorial. Combinatorics probability cannot say anything about, so we're hoping for geometry to explain. But you can also, so suppose that somehow you are able to simulate this, although we cannot really simulate this for the same reasons. So what is a typical permutation gonna look like for these pipe dreams? If, let's say you sample them uniformly at random. We don't know that either. And what is the maximal permutation? So for which permutation do we get the maximal number of pipe dreams that connect? So here we have a guess. And so some people in the audience actually have done some experiments. So maybe this would be something called layered permutation that I will define. Okay, so that's one very difficult model. And so there was this other discussion yesterday. So how, what stands above this whole thing? Well, let's try to relax the model a little bit and now allow the pipes to cross more than once. So now we are looking at all possible tilings. So 2 to the n choose 2, because for each square we have choice 2. And but you're gonna read the permutation a little bit funny. So you're so the tiling is the black lines here, but the colored lines are how you are going to resolve the intersections in your mind. So how to track where the permutation goes. So there is some rule how to resolve this. How many are there? Well, 2 to the n choose 2. What does a typical permutation look like? And suddenly we can simulate this, because we can actually sample uniformly random tiling just by picking the boxes. And then we can read off the permutation by an algorithm. So we can see what a typical permutation looks like, and the typical permutation looks something like this. So how to read this? This is like a permutation diagram. Here are the ones, and ones start from here. So most values of the permutation would be concentrated here and on this semicircle, quarter circle, really.
So you're reading it as like a permutation matrix?
Yeah, so you're reading it as a permutation matrix. So at some point in the talk, unfortunately, I'll switch the graphs, but wherever this sharp corner is, this is like 1, 1. So you're reading it as a permutation matrix, and this is what's called a permuton, is where you sample a lot of these permutation matrices. You put the ones with some very small intensity, and then you stack them all together. So where you have a higher intensity, that's more, and there you see more ones in the permutation matrix. Yeah.
So I'm guessing it's unsatisfying for some reason on the left side to color your pipes and say that not, so I would no longer have just 2 tiles, I'd have like n squared.
Yeah.
So many tiles.
Yeah, because the number of tiles is also growing with infinity, we still cannot analyze. So yes, this is a colored vertex model. So there is a way to study this, but because the number of tiles is also growing, you can't really say anything in the limits. That's the short answer. And for which permutations do you get the maximal number of configurations that give you those permutations? It turns out in this case, the layered do give you maximal. So this is asymptotic maximal that we're talking about. It's not like the absolute maximal. So that's, yeah.
Let me check if I understand this picture. So you took the 2 to the n choose too many pipe dreams. You, each one turned into a permutation. You added those up and you got that?
Yeah,
Okay.
basically, well, so we sampled it, so we didn't really go through all possible 2 to the n choose 2. We just like simulated a lot of them, and that's what it comes to. And if you pay close attention, you will notice that the maximal ones, I haven't shown you the picture yet, do not fit that that's him. So there is something funny going. Okay, so this is, as you already know, so this is the Schubert setting. These are the Schubert polynomials, model for Schubert polynomials that are undefined. This is the Grothendieck polynomial setting. This is the K-theoretic setting. You can define the Grothendieck polynomials on those pictures. I will show you how. And they contain in themselves the Schubert polynomials, but many other terms as well.
Okay, so the measure you're getting on there is like, has like this delta function along that curve.
Yes.
Cool.
Okay, so then we have a formula for that picture. Don't worry, it's gonna get there hopefully. Okay, so since we're already up to speed here, I'm not gonna spend much time defining the Schubert polynomials. Is that okay? So they can be defined recursively with this divided difference operators, starting with this monomial for the maximal permutation and then going down by sorting our permutation. It's a very nice definition, but it doesn't tell you anything. In fact, it doesn't even show that this is a positive sum of monomials, as what I can see. There are, of course, some special cases. The Schur functions are nice, but they are a very small class of permutations for which we have such nice properties. And this is the model that I showed you earlier. So let's just make sure we're on the same page. These are the reduced pipe. We will call them reduced pipe dreams or RC graphs, which are, Schubert polynomial is equal to the number of all these configurations that give you the particular permutation. For each row, you count how many crosses you have, and that's what's gonna give you a monomial. So, of course, in that case, it's gonna be a huge sum, so we are not gonna go through all of them. And Schubert polynomials have some nice properties. So for example, there is McDonald's identity if you plug in ones. And in particular, if you plug in ones, what are you doing? You're counting the number of pipe dreams, whereas for each pipe dream you get a 1. And it's equal to 1 over the length of the permutation, so the number of inversions factorial times the sum over all reduced words of this product. And then you have some other nice properties like this Cauchy identity, for example. So you take two sets of variables and you take sort of the opposite permutation, you multiply the Schubert polynomials, you get this nice product. So let's remember the Cauchy identity for a moment, because this is going to be our starting point really for any type of analysis. Okay, so Stanley in 2018 posted a paper on the archive with named Some Schubert Shenanigans, which had a bunch of interesting conjectures in them. Most of them got solved except this one. So he was wondering if you take the maximal Schubert polynomial when evaluated at once, or in other words, the number of pipe dreams that give you a particular permutation, he observed that this is growing exponentially in n squared. But how? Like, what is the constant of that exponent? Or in other words, if you take logarithm with base 2 or whatever else, and you divide by n squared, does this actually approach limit when n goes to infinity? And from a asymptotic point of view, actually, it doesn't matter whether you look at a particular permutation or just the number of all graphs, because the number of permutations is only n factorial, which is much less than 2 to the n squared, which is the main contribution that's coming here. So asymptotically, the rates of growth would be the same, whether we look at the same one permutation or the whole thing, so might as well not restrict ourselves. And how he figured that maybe such a limit should exist, because the Cauchy identity tells you that the sum over all permutations, these products, is 2 to the n choose 2. There are n factorial many permutations, so the maximal Schubert polynomial, which is in there somewhere, is on the one hand bounded by 2 to the n choose 2, on the other hand is bounded from below by square root of 2 to the n choose 2 over n factorial, let's say, but disregarding the n factorial, you get a bound for this C, 1/4 and 1/2. And now, so how do you approach this problem? Either you look at all RC graphs, at least to get that such a C exists, so we don't know that it has to exist. I mean, it might be some number theoretic thing going on, and this is oscillating between different values for different n. We don't think that's the case, but there is no proof that the constant would exist. And then which permutation give you the maximum? So one thing that we did is we looked at so-called layered permutations, and it turns out you can actually analyze asymptotically the value of the Schubert polynomial a little bit better then, and you get a better lower bound than what Stanley had of 1/4. You get 0.29 whatever. And in particular, we can say from those class of permutations, so the layered permutations just look like these blocks of reverse permutations. So the parameters are just the sizes of the blocks. These are the B's. And it's so they are just scaled one from each other, so they form a geometric progression, these sizes. This would give you the maximal layered permutation and that particular value for the Schubert polynomial. So now the lower bound is, we know at least 0.29, whatever. So how did we get there? So, okay, so before I say that, so there is a conjecture that this would be the maximum, but the conjecture is, so Dave was saying how how large was the sample that you checked it for? Like n equals to 11?
11 it checked, but Anders tells me I was doing it wrong, so maybe maybe I should be able to do more.
Okay. But also
Yeah, that's a
you had a student that was checking this at some point earlier and yeah. So state of the art is, let's say, n equal 10. I think for up to 10, it was checked that the maximum is achieved with layered permutations. Maybe n equals 11. And so from a asymptotic point of view, that's nothing. That's nothing, but it's not clear what the evidence is here. Okay, so maybe this is the actual maximum. We have another upper bound, better upper bound than 1/4, and this comes from the alternating sign matrices that Sarah was mentioning today in her talk. And this is because of these bumpless pipe dreams. They are bounded from above by the number of alternating sign matrices. In particular, so is the principal evaluation of the Schubert polynomial, and for the alternating sign matrices, we have this beautiful formula, which is asymptotically to the 0.37 whatever n squared. So that's a better upper bound than 1/2. So we know that the quantity in question is in between 0.29 and 0.37. So where exactly is it though? And indeed, so the first thing is just to prove that there is such a constant. So how did we prove this? I'll just show you very briefly. So for layered permutations, one can write a product formula essentially for the evaluation of the layered permutation, and it's products of terms that look like this. This is itself a very curious identity. This is actually the number of plane partitions of triangular shape bounded by M or 2M. And so recursively, the Schubert polynomial, when you split your permutations into blocks, it splits into these products. So in those cases, we have some type of a formula, but of course, analyzing that formula itself is not so easy. And so we need to approximate it by some function we can analyze. So that's one function. So if you do the Riemann, if you approximate this with a double Riemann sum, take the logarithm, you approximate it with a double Riemann integral, this is what you get, and you really need somehow very tight bounds in order to do the induction properly. But you get some kind of explicit function, and you need to solve an optimization problem sort of by induction. So you know that the smaller block of layered permutations would be maximizing that Schubert polynomial, and now you're solving inductively of the problem for the maximum. This is this Vn maximum for smaller plus the log of this term. So what is the ratio between m and n that give you a maximum? And you end up with some differential equations for this horrible function, and this is where this gamma and alpha are coming from. So there is no combinatorial meaning as far as I know. Just comes out from the analysis calculus. So you can compute it numerically. And so then this is again our answer. Of course, you need to make this argument a little bit rigorous that you can do this asymptotic analysis like that, but in the end it's just some calculus. In the end it's some calculus. Okay, so this is as far as we get about Schubert. So we were wondering, how can we understand whether we are really on the right track, whether these layered permutations really are are giving us the maximum. And one way to approach this, at least heuristically, is to look at some generalization of Schubert polynomials, which is the Grothendieck polynomials.
Just to clarify, layered permutation means like longest element in like a young subgroup. Is that how I should think about it? Like there are blocks and I take the long.
So
That you get.
So the layered permutation is just, this is what the permutation diagram would look like. So you take blocks.
Yeah.
And in each one you take the longest element.
Yeah,
reverse
so
it.
it's a, you
Yeah.
have like kind of a young subgroup,
Yes,
maybe not
yes.
in the usual way. But okay.
Yeah, so you take a layer, a young subgroup and you take the maximal elements in each. So if there is a geometric argument that would tell you this is where the maximum is, then maybe there is something.
But are the block sizes specific?
The what?
The block.
And the block sizes are specific, they come from this alpha.
Okay.
Yeah, so asymptotically, of course. So everything here is done asymptotically. We cannot say the absolute maximum is whatever.
Yeah, because I guess
Yeah.
you could do one big block, but that's obviously not maximum.
Yeah, so that's
The point is
exactly.
you have to have weird block size.
Yeah, you have to telescope this in some sense, so you're like, it's kind of fractal structure because if like the big block and then the same picture repeats itself in the smaller blocks and the smaller blocks for yeah.
And alpha is something like the slope of that red line.
Yeah, and the slope is the red line here, yeah. So, okay. So let's go to the Grothendieck model. So again, so there is a lot of geometry and K-theory behind the definition. I'm not gonna go through it. You guys know it better than I do. Here is the definition in terms of divided differences. So in this case, the De Mazur difference operator, there is a beta parameter in the whole story here. And there is now the pipe dream model, where now we are looking at all possible pipe dreams with double, triple, or whatever intersections. The way we read the permutation that we are looking at is we go over the pipe dreams, maybe like diagonally like this. So every time we are about to make a second intersection between two pipes, we imagine that they go in the other, follow the other branches, and then we color it like that. We resolve all the double intersections and we get some permutation, and then we basically now we restrict ourselves to looking only at these pipe dreams that give you this permutation. In the end, you go over those and you have some generating function beta to the minus length of the permutation, and then for each intersection on the original one, right? So this time you'll have more intersections than you have inversions in the permutation. For each plus you have a, you take a beta times xi is the variable for the corresponding row. And when you set beta equal to 0, everything but the reduced pipe dreams will die, and then you just recover the Schubert polynomial. So in some sense, this is like an interpolation from Schubert to a more simpler model. So we cannot really access this in full beta generality for beta, but if we take beta equal 1, so it's sort of another end of the spectrum, we're interpolating, then we have some nice properties. So let's take beta equal to 1. The number, just the sum of these guys, is just 2 to the n+2, as I was saying, all the possible tilings. So in particular, we already know what the maximal value is here. So the maximal value for the Grothendieck polynomial beta equal 1 is just 2 to the 1/2 n squared minus of n log n, but lower order terms. So now what do we want to know? Or which permutations is this maximum achieved is the first question. And again, so we are kind of trying to reinforce our idea that maybe the layered permutations give you maximal Schuberts. Let's check what happens when we take layered permutations here. Is this going to be a maximum? And you do some experiments, including the student did the earlier values, and so there is actually a determinantal identity that would help you to compute this faster. And you get these values for the layered permutations, and the layered permutation, again, you have some ratio of the sizes, maybe 1 over square root of 2 in this case. So at some point we thought we were getting some Fibonacci sequence, but that was a little bit of an artifact. But as you can see from the values, it's converging to 1/2. So it is getting close to the maximum. So now let's try to prove this. And so we actually can say this, at least asymptotically, that the layered permutations do give you maximum. And in fact, you are kind of free to choose how big the layers are, as long as the ratio of these pieces is within the interval 1 over square root of 2 to 1. So where did this come from? So as I said earlier, there is a determinant, I'm not going to show you that computes this. It's of shifted Schroeder numbers. It's a huge determinant, and in general, it's hard to analyze asymptotics of such determinants where everything is growing. But we can use some tools that are already in the literature. And for that, I need to show you the other model for Grothendieck polynomials, and this is the bumpless pipe dreams. Again, that was mentioned, so I'm not going to repeat this. So this time you have 6 tiles, and it's not exactly a tiling because you need the tiles to connect properly. So they have to match with each other. And if you don't impose anything, this actually corresponds to alternating sign matrices. If you don't impose any conditions on how many times they intersect. But if you want to determine what permutation you get, you need to resolve these pipes with this forbidden tile here. Then you will follow the pipes and figure out which permutation you get after you resolve. So this is a model. This is in particular this model, and we have a theorem due to Anna Weigand that the Grothendieck polynomial is equal to all these bumpless pipe dreams that would give you after resolution this permutation. And then you get some monomials. How do you determine what you get? So if you first look at the empty tiles, for those you get beta x, whatever the row of the empty tile is, and then you have for the northwest bumps, so this inner type of corners of in our pipes, you get 1 plus beta xk. So when you plug in everything to be equal to 1, you are like counting these configurations. And let's forget about so for a moment, forget about the permutation, but you're counting these configurations with 2 to the number of these guys. Right? And that is the formula, and in particular, okay, so ASMs, but with special the ASMs that would give you this permutation. So there is something missing in the right-hand sum. So how does the correspondence work? So here is one of these models, and we've drawn it a little bit differently. Again, this is a bumpless pipe dream that's giving us some particular permutation. You replace the inner corners, so these corners with a 1, the inner corners with a -1, and everything else to 0, and you get exactly an alternating sign matrix. so alternating sign matrices are very difficult when you are counting them without any weight, so uniformly. But they're actually nice when you count them with a factor of 2 to the number of -1s that you see. This is what's called a 2 enumerated ASM, because this is in bijection, sort of like. It's so-called domino tilings of the Aztec diamond. So pictures that look like this, we're tiling with a rectangle. It's a shape which is called Aztec diamond, but it's really just a cube, rotated cube on the square lattice. And now we take it to the limits. That was one of the first results in the integrable probability, the limit shape of the Aztec diamond. It goes back to so Elkis, Larsen, Probe, Kohn, and Kenyon, and so on. So all this work, that you get a limit shape. So everything, the interesting stuff happens here, and everything here is frozen, basically. Which in probabilistic terms means that with probability almost 1, you get this type of tile in these corners. So that's already a result in the literature. What does it mean for us? So let's go back to transfer the whole picture with the bijection to our bumpless pipe dreams. It is telling us that something's going on in this circle, but outside of the circle, things are fixed, essentially. And then you get pipes that look like, so here is empty, whatever, here are process only. And then what does it mean that you're getting crosses here? It means that in this part, your permutation is basically fixed to be the reverse permutation in this lower corner. So with probability close to 1, you are getting something's going on here, but the last part of the permutation is going to be reversed. And then you can use this to asymptotically count the number of configurations for the layered permutation this way. I'm not going to go through all the derivations, but basically you get that the number, if you take like identity and then reverse permutation is asymptotically 2 to the n choose 2 minus 2 to the k choose 2. And you get some expression for the Schubert, for the Grothendieck polynomial in terms of these binomials and the sizes of this, of the layers of the layered permutation. And then you can optimize this and say that the max, so as long as the layers fall within 1 over, as long as the layers are small enough to fit in here, but this is just 1 over square root of 2, then you're getting this maximum.
Are you telling us, wait, you showed us in like the first set of slides, the boundary of the typical permutation? Are you telling us it's a arc of a circle, or?
It is the arc of the circle, but it's not that circle. Yeah, so there are a bunch of coincidences going on here that are kind of come from the probability in the ends, but there is no actual connection between them. So now I'm going to tell you about this arc of a circle that you're asking. Okay. So anyway, but the punchline is that we are using this classical result from integrable probability to extract the information about the asymptotics for this Grothendieck polynomials, and in particular we can say that so the layered permutations for some parameters are indeed maximizing asymptotically the Grothendieck polynomial, so maybe the whole correspondence goes true, and this is indeed going back to Schubert. But unfortunately for general beta, there are a lot of subtleties involved that we cannot apply this type of reasoning. So now we can talk about this wedge this pizza slice that was in the first slice with the delta mass. So how do you get that thing? So how do you analyze the typical permutation? And to make things a little bit more general, now we're going to go on to a tiling model where we put tiles with probability P to be crosses and 1 minus P to be bumps. And then to get a particular permutation out of the whole thing, so once you do the resolution of pipes, it's going to be equal to this value of the Grothendieck polynomial, evaluated at P over 1 minus P. And then you run your simulation. So this is n equals to 2000. So sorry now, because this is mathematical plot. So normally the ones come from this corner. So this is not a permutation diagram. This is just a first quadrant type of plot for our permutation. But this is 1 is over here, and sort of this wedge is the reverse permutation. This is one permutation sampled out of this. So the dots correspond to where the ones are in the diagram. P equals 1/2, you get this, and then you simulate it many times and you get your points with low intensity. So this is like a density plot of that picture. So how likely is it to get a 1 in this spot? The darker the color, the more likely it is. And then there is a delta mass, as Alan observed.
Sorry, was there a P in the last picture?
The last picture, there is no P, so then the P is 1/2 in the last picture, but in the other, yeah, we can draw these pictures for different P's, so it would be exactly whatever you see here, but like shaded. Yeah.
Are you naming that shape, the permuton?
The permuton for this model, permuton is just like a limit of permutations. In that sense, that's how you can think about it. That particular shape, we didn't name it. We were calling it ice cream cone at some point. But actually, so Leo was running the simulations. You can put not the triangular grid, but some other grids in there. And then you can get some really weird shapes for this permuton, but that's different. I mean, this will only come from the simulation, and it's not something we can actually analyze, really. So you can play a game of doing this and see what kind of permutations you get. Okay, so what is this permuton that we're seeing? How do you describe a limit? What something looks in the limit, and so in integrable probability, one of the ways is to take something called the height function. And in our case, this is going to be some observable that's kind of continuous. So the permutation is a very discontinuous thing. So you change values, the dots go all over the place, but you can kind of smoothen it out by taking this statistic for 2 points x and y. I'm going to count how many entries in the permutation diagram are in that shaded rectangle. So now this becomes a little bit more. So this is now a monotone function in x and y, and you can talk about what it looks like in the limit. So that's the property of the height function. And you can scale it with n so that it just fits in a 1x1 square, and you get some function like h0 in the limit. So this is something we can prove, and I'll show you maybe a little bit what this function looks like. And in fact, we can even say what the fluctuations are, in the sense that what is the probability that you are moving out from this average that you get with some scaling factor, which in this case has to be n to the 1/3. And turns out this is the same probability as the probability that a random permutation has a longest increasing subsequence equal to whatever. This is the Tracy-Widom distribution. So for the moment, we have no algebraic explanation of why these are the same. It just comes out from the computations. And it might be just one of these artifacts, right? So there is, in the limit, many things start to look alike. Yeah.
I'm seeing a lot of jargon words in the theorem, I guess. What's a KPZ universality class, for example?
Ah, sorry. Yeah, so that's okay. So took the theorem from the paper, of course, and this is because I mean it was a kind of aimed more towards probability. So in integrable probability, the KPZ universality class is a class of models which in the limit are governed by a certain set of differential equations, PDEs. And KPZ is Carter-Parisi-Zhang. This comes from physics, and this is one class where you see some types of what they would call universal behavior in the limit. So in particular, this model belongs to that class. And it's one of the problems in statistical mechanics is to show that various models belong to that class. So they have universality in the limit. So in the particulars of the discrete situation, what it looks like might be different, but in the limit, they all look the same. So that's the short answer to the story. And in particular, what we are saying here is that probabilistically in the limit, this is behaving like many other problem objects that show up in statistical mechanics. So what does the limit shape look like? So this is for p equal 4/5 or something like that. These are the plots. Although here it is again p equals 1/2. So this is sort of what the limit shape looks like in 3D in that region. So the parts outside we can. And it's a bit difficult to see, but they're supposed to be flat. And this is the equation for the limit shape. So whatever this surface we are getting, these are the equations. And there is a region where this region see where things are happening, and the region from one side is for general P, it's going to be an ellipse that is bounding this thing. Ellipse is given by this equation. If P is 1/2, we just get a circle. And now you can also, using that limit shape and the properties of the permuton, that the statistics for the permutation, like let's say number of inversions or any other pattern that translates in the limit, we can say that the inversions, for example, for this random Grothendieck permutations, can just get them from integrating whatever this limit shape was. And well, the integral is not very simple to solve, but in the end, you get some expression of that kind. In particular, where P is equal to 1/2, the number of inversions is 1 minus pi/4 times n squared over 2. So, and okay, so I can say very, very briefly how one analyzes this to begin with, how you get such a result. And it goes through an identification. So there are many steps that one needs to take. One is what Alan already hinted at, there is a colored vertex model. So if you color all your pipes from 1 to n, you can keep track of all the intersections this way and whatnot. And this is what is called in statistical mechanics a vertex model. So you're looking at all possible configurations which kind of fit together with various weights. Then in terms of the vertex model, your height function can be expressed. And you can, but if you want to just analyze the height function from x, for how it behaves for x, y, we can forget most of the colors. You can just make it what's called a color blind, in the sense that we only care about if the number smaller than x go beyond the value of y. So if we just wanted that statistic, then we can forget about what colors and what are the pipes smaller than x or bigger than x, as long as they're two different colors. And then things simplify a lot more. So don't read all of this. So that's a little bit more detail than you probably want to know. But when you have this so-called colorblind model, then you can pass to what is called the TASEP, which you might have heard in various settings. This is the totally asymmetric simple exclusion process. Or in other words, these are some particles on a line that are hopping with various rates, and they are not allowed to go past each other or hop on top of each other. And then this is some kind of a process that evolves with time. So here are it is really a Markov chain, but you can picture this as beats on a line, and every next step, so these particles cannot move because this guy is blocking them, but this guy can hop. So on the next level, this guy hops, then this guy can move, and so on and so forth. So you have this lines of dots of particles that are moving somehow in that direction. And and so that goes through all these correspondences with our model. In the end, we want to know what is the various exit probabilities. In our case, we're going to have a staircase shape, so we're going to care about when do particles get out of that red line. And in terms of how things look like on our pipe dreams, these are the original pipe dreams for the Grothendieck. We're not going to care about the double intersections in this case, just because we care about where are these guys going with respect to this line. Whether they do have some double intersections or not, it doesn't matter, because they'll get into the same place in total. And this is, on this particle picture, this is what these jumps look like translated on the particle model. And so now there are a lot of tools to analyze TASEP, including the various exit probabilities can be computed using Schur functions. And one does an analysis of asymptotics of Schur functions to get what this looks like with this particular exit boundary. So I'm not going to go through all of this, but in the end, you get functions, limit shapes that look like this, and this actually in particular, you can also do the smaller scale asymptotics. You get this F2, which is Tracy-Widom distribution. And this will give you the fluctuations. And so here is back the results. So this H0 was something specific, and F2 is what's called the Tracy-Widom distribution, which is also going to be the distribution of the largest eigenvalue of a random unitary matrix. And this is what our permuton looks like. And so, do I have 5 minutes or not? Yes. Okay. So, so this is how, without really going into the details, one analyze what a typical permutation would look like under the model. You notice that this is not the layered permutation in the permuton. There's not a contradiction. So the layered permutation is the one for which the probability is maximal, but on the other hand, can think of the probability as some graph where maybe here this is maximal, but the bulk looks like this. So overall, these probabilities are bigger altogether. So that's why you get a different shape. And in some sense, the probability, in some sense, this will cover the layer permutation, but they are very small contribution together. So you wouldn't really see that on this picture. So there is one other model that actually people ask me about, so what happened with that? So this is a picture from Stanley's birthday conference. A lot of you guys were there. There were open problems, and Colin Defant is his elbow here, sir. Came to ask an open problem. So he drew these pictures on the on the slides. So you already saw this, but you have some intersections here. So now he was asking the very simple, I would say naive model, in the sense that this is what you would do on this without relation to algebra and geometry. If you do a tiling, so you have these tiles again, probability P and 1 minus P, and just follow the pipes. You get to some permutation. So you don't do any resolutions, you don't impose any other global conditions, just simple following the pipes. What's the resulting permutation going to look like? And in particular, what is the expectation of the number of inversions? And what are the statistics of the permutation going to look like? And so now, in order to analyze that, you don't really need to go through all the machinery that I was showing earlier, because you can find exact formulas for one pipe to go somewhere else, since we actually don't really care how much it interacts with the other pipes. This is more or less a random walk with some reflection, and going straight, the probabilities are going to be what's the probability of a reflection, what's the probability of going straight, but you can guess a formula in some sense and then prove it recursively. And you are conditioned to stay in this triangle, so you have some like reflection principles telling you how to keep the pipes in there. You can get an exact formula. Unfortunately, that exact formula is not actually telling you anything about the inversions, because this is the probability just for one particular permutation. But there is something else you can analyze, and which is what is the displacement. So what is the probability that I goes to I, or farther away from I? So how far are the values of the permutation from their origins? And that we can actually compute explicitly using these formulas, or just some general considerations. And it's not so hard to see that the number of inversions is bounded by this displacement of the permutation. So you can at least say that, in particular, the expected number of inversions is whatever this is, the way it's going to be, n to the, we're summing over all possible I, in the end you get n to the 3/2. This is in contrast with the other model, where the number of inversions is on the scale of the model and squared. So in particular, there is no point in talking about a permuton here, because you're basically close to the identity permutation all the time. So that's not something we'll draw. So we get a bound for it. And then Colin Defant went and solved his own problem. So he did a more careful analysis of how two pipes would interact with each other, and to prove that the number of inversions is the geometric mean of the two bounds, actually. how come it came to that? It's not exactly clear. Is this some artifact again of probability, or is there some deeper meaning in the combinatorics? And on that kind of.
Any questions?
Yes.
Yeah, so two questions. The first one is, did you ever look at varying the probability based on the box location? I think the most natural would be the row. So like you do a Q analog, say, so first row occurs with probability Q, second with Q squared, and so on.
That one we didn't do. That's a good idea. We had another condition about Q, the likelihood of resolving a pipe at some point.
Okay.
But that's also not so easy to analyze in the end. So
Yeah, I know there's nice results about principal specializations of Schubert's, maybe with respect to the Q analog. So with Grothendieck's, that seems plausible.
yeah.
And then the second question I had is, there's a paper from 2009 by Angel, Holroyd, and Romick, the oriented swap process. And it feels like a lot of what you guys are doing is very similar because you're computing a Demesure product of a random subword here. They're doing a Demesure product of just a random word.
Yeah.
And so I wonder if there's any way to relate the two models. Right, so if you wanted to do it maybe on a rectangle rather than a triangle,
Yeah.
I wonder if you would get the same behavior that they observed.
Right. So they're doing random sorting network essentially, but with different.
They're just
ways.
saying pick a random SI between 1 and n-1 at every time step.
I see.
So it doesn't have the same structure that you guys do where things are.
So we looked at that, we couldn't really find a direct connection somehow.
Okay.
The geometry of where you are doing these things really changes.
That makes sense, yeah.
And we couldn't really find a good correspondence to use those results.
Yeah, I'd be curious if you did it, like I said, on a rectangle
Yeah,
instead of triangle,
so
whether they maybe would line up.
that does make sense. So one can run the simulation on whatever you want, basically. That's and get various different permutons and shapes.
I'm always curious about the thing in McDonald's formula. It's a product of the letters in the reduced expression. So did you try?
Yeah, it doesn't work. So that was my the first thing I tried. One of the problems with McDonald's formula, that the number of summons is huge. So, and that actually contributes to your asymptotic. So when you have a sum of a product, you want to do asymptotics out of it, you need to have the sum relatively small to what the maximal product would give you. In McDonald's identity, the sum is too big. It's like the order of magnitude is beyond what the asymptotics will.
So not so much for the proof. I was wondering more if you use that as a statistic of interest. So if you take a random pipe dream, it has a reduced expression that goes with it. You could multiply together the numbers. What's the distribution of those numbers?
It's a good question. We haven't checked. Yeah, that's another. But so when we talk about reduced, if we go to the Schubert, we cannot simulate anything. So we cannot run the simulation. We can only run a simulation on Grothendieck model, and I'm not sure how interesting that would be. That would be the Demesure product. So.
You get a 0. It's not.
Okay. Just one.
Can you sample the super polynomial situation by just picking a Grothendieck pipe dream and then finding the reduced ones and then figure out how many Grothendieck pipes with the same one, then divide by the number of those ones with your weight? It might just take a long time.
Yeah, I'm not sure we can compute any of those things. I mean, okay, so we can start with a sample from the Grothendieck model, but from there on it might.
I think everything is easy to compute. It's just a matter how many there are.
Yeah.
Huge number of Grothendieck pipe dreams that contribute if it takes too long.
Yeah, so unfortunately, there are too many somehow, so I don't think we. Yeah, then they're gonna vary. Depending on the permutation, you're gonna get a different scaling sort of. So it's, I'm not, yeah.
Okay, just one more question.
I guess this means we also don't have a fast mixing Markov chain on reduced pipe dreams.
No.
Okay, thanks for speaking.